All right. So we left off with SN1 and SN2. And so today we're going to start elimination, and I'll send these videos after class because I don't think I sent them yet, but I'll send the elimination stuff today. And then on Wednesday and Friday, we're going to go through the rest of this handout. There's a bunch of problems that we're going to solve between Wednesday and Friday. And yeah, and then we'll move on to another section. So the next exam is going to cover whatever we cover here, substitution and elimination, and then whatever we cover from, I think the next section is like conjugated diene. So it's like two different reactions in that section. So, but let's jump back in here with this elimination. We're going to talk about E2. And the thing about the E2 elimination is it kind of follows a similar path. Well, not a similar path. Let me take that back. It works under the same criteria as the SN2, with the exception of the substrate structure. Because you can see right here, right, a tertiary or secondary carbon is favorable for E2. We're going to talk about why. I'm actually going to work that second example this time instead of the first one. So I can show you all the features of it with one example. Aprotic solvent still, that goes without saying, especially when you have a strong base present. If you have a strong base present, you put it in an aprotic solvent, the base is not going to do elimination, it's just going to do proton transfer with the solvent. And it has to have a strong base present, and it follows what we call Zayt's rule. So we're going to talk about all that.
Oh, yeah, I got it. I had to do something like this.
Let me cut this out and put it on a different page. We're only going to work. So this one I might have you do on your own, the top example, and I'm going to do the bottom example. So let me just cut this out. Page. So we're going to take this. Right here. All right. And so with this example, we're going to look at the E2. One of the things about E2, again, is you need a base, in this case, KOH. I think on the list, do I have a list of bases in here? No, it's not in here. I have the E2 video that I send you. It's going to have a list of bases, but some common bases for E2. You can use KOH, NaOH, butyllithium, and I'll write that out so you'll potassium terbietoxide is another common base that you'll see, and this is very bulky, really strong base too. Looks like that. So those are some examples of bases that are used to do E2 elimination. But that's a requirement. You can't do E2 without a strong base. So you have to have a strong base present. If you see the presence of a base, one of these bases or some other base, then you know that you're doing an E2 elimination, right? That's a dead giveaway. A base and an aprotic solvent like dichloromethane, DCM, that's another dead giveaway. All right, so with elimination, if you recall from organic 1, when you're doing elimination, you always get a pi bond in the product. And so here, what we need to do when we're thinking about elimination reactions is, first of all, identify my leaving group. Once I find the leaving group, which again is going to be more than likely the most electronegative atom or functional group. When we find that, the next thing to do is identify what I like to call the alpha protons. So those are the hydrogens that are adjacent to, we'll make the other one a different color, adjacent to your leaving group. Right, the hydrogens that are on carbons adjacent to your leaving group, right? Because this is a carbon right here, that's a carbon right there, right? So with the elimination, once you identify the leaving group and the alpha protons, let me write that in. Right, so those alpha protons are on carbons that are adjacent to your leaving group. So once you identify those, you know where the elimination is going to take place. Once you identify those alpha protons, right, the elimination is going to take place here. So you're going to end up with a pi bond here and one here. So you're going to end up with multiple products, especially in a scenario like this where your leaving group is between 2 carbons and both of those carbons have a proton that can be removed using the base, right? So those 2 sites are where your elimination is going to take place. So the base is going to come in. We'll just go through the mechanism real quick, how this works. So this is my base, right? It's going to come in and attack one of these protons. Uh-oh, what did I just do? Sorry about that. I don't know why this app is tripping. It's going to attack here and do proton transfer. And then that proton, once it's removed, is going to donate its electrons here to make that pi bond, because we're trying to make a pi bond right there. And at the same time, I'm going to lose my leaving group. So that iodine is going to leave with a pair of electrons. So just like the SN2, the E2 is concerted. Man. All right. So the E2 is a concerted reaction. Just like the SN2. So when the base is coming in and removing that proton, same time the pi bond is forming, and at the same time the leaving group is leaving. All 3 of those things are happening simultaneously. All right. And so what that's going to give me product wise, uh-oh, I think I screwed that up. Hold on, I got one extra carbon in there. Is a double bond here. I mean, right, and then this terminal carbon is still, it's untouched. It's not gonna make them both together, but they'll be formed at the on the same molecule, but not at the same exact time. So the other side will get deprotonated by a different molecule of hydroxide. All right, so that's one of my products, and then the other product, the hydroxide is going to come in from the opposite side and pull off that pink proton. All right, so this is negative. This is coming here like so. Boom. Same thing here. And I'm losing a leaving group. Right. And again, this is happening not simultaneously on each proton, but on another molecule of that substrate. That's where the second elimination is going to happen. All right. So don't think it's happening where you're going to get two double bonds in the same product. That's not going to happen. All right. I'm just going to cheat and copy this. Right, I'm gonna erase this alkene and put the other one in on the other side. Right, so that's my product from the second elimination. All right, any questions about that? Dang it. All right, so let's talk a little bit more about these products and also about one of the key characteristics of the mechanism. So with the products, these are, again, if there's a competition, there's going to be a product distribution. And so for any elimination, it's going to follow what's called right here, Zaitsel's rule. And what that means, or that not what it means, but what the rule says is that the more substituted alkene is going to predominate. All right, so when you do an elimination and you have to figure out which product is major and which is minor, you base that prediction on Zaitsel's rule. So the product here is going to be major, and then here is going to be minor, because the most substituted alkene is going to predominate. So you have a alkene that's tri-substituted, which is the one here in pink. You can see it has 3 groups on it. We talked about this before. Right, and then down over here, this alkene is di-substituted. All right. So for Zaitsel's rule, the more substituted alkene predominates. It's a thermodynamic characteristic, because the more substituted alkene is also a more stable alkene. All right. So that's one characteristic of the E2, is that it's going to follow Zaitsel's rule. Another thing about the E2 is the geometry. Like there's a necessary geometry for elimination to happen. And I'm going to show you that. The geometry that's required is what we call antiperiplanar. right? So I'm gonna show you this on a generic alkyl halide. So we have something like this, right? And I have my leaving group here, right? On the alpha side, which would be here or here, those protons that are there, the alpha protons have to be opposite of the leaving group, but in the same plane. And the easiest way to illustrate that is to do a Newman projection. So I'm gonna draw this. I want to draw it in terms of this carbon and this carbon, right? So we're gonna make the carbon where the leaving group is the front carbon. So that's here. So I'm gonna put I'll put my leaving group on that carbon. So my leaving group is here, and the other pieces to this carbon, there's a hydrogen on it. Obviously, I'm gonna draw it as a staggered, and then there's a CH3 group here. And then the back carbon, the other carbon that's circled in red, I'm gonna draw that here. We'll draw it as a Newman projection, right? So that carbon has 2 hydrogens, and then another. Let me not put that CH3 over there. Right? And so this is what we call a Newman projection. All you do is take 2 carbons in the chain and basically look down the carbon-carbon bond. That's how you develop or come up with what the Newman projection would look like. So the idea is that the hydrogen here and the leaving group here have to be what we call, again, antiperiplanar, opposite sides of the same plane, right? And so in order for this to eliminate, this is the orientation that the hydrogen and the leaving group must adopt, right? They have to be anti to one another. That just means they're on opposite sides. Right, and the reason for that is it's an orbital argument. And so when that proton is getting pulled off, in order for those electrons to be shared with the carbon where the leaving group is, right? In order for this to happen, and for the leaving group to leave, right? Those electrons have to be able to donate into what's called a sigma star orbital. So that's right here. So the carbon leaving group sigma star orbital has to be accessible to that pair of electrons. And so that's why the geometry has to be antiperiplanar, so that the sigma star orbital can be accessible and the electrons can donate into it and facilitate that bond breaking between carbon and the leaving group. Right, but that's kind of beyond the scope of the class, but that's the reasoning behind why it has to adopt this geometry. So anytime you do an E2 elimination, right, there's a geometric requirement that the leaving group and the alpha proton be antiperiplanar. All right, and there are some rare cases where that's not possible, especially if you have like a chair, a ring, 6-member ring or something like that, and it has a large substituent that prefers to be equatorial. But if it's equatorial and the leaving group is axial and you can't get the right conformation between them, the 2 carbons that are going to be involved in elimination, then it won't happen. But it's rare. All right. So for E2, the thing to remember is that there must be a base present. You have to do it in an aprotic solvent. We already talked about that. The geometry is antiperiplanar between the leaving group and the alpha proton, and the product is going to be based on Zaitsev rule, right? So it's going to be The more substituted alkene is going to be your major product, the less substituted alkene, the minor product. All right, questions about the E2. So you'll do this one on your own, the one up top. It's a lot simpler because you're only going to get one product because all those methyl groups are identical. All right. If no questions, we're going to move on to the E1. And then we're going to start doing, we've got plenty of time. We're going to start doing some examples. Let me just cut it out. Fix that. All right. So E1, totally different from E2, even though it's still an elimination. Same criteria, tertiary, secondary carbons. Difference here is that it actually works in protic solvents. So it's similar to an E1. The mechanism is in that you lose your leaving group first. That's your rate determining step. And then after that, that's when the elimination happens. All right. Obviously, it's going to favor tertiary carbons because if your leaving group is leaving and you're making a carbocation intermediate, you prefer it to be tertiary because that's the most stable, right? It's going to still follow Zaitsel's rule, and again, the mechanistic pathway is very similar to SN1 all the way up to the elimination step. So I'm going to draw the product in here, and then we're going to talk about how this happens. And if you notice, there's no base present. You actually can do an E1 elimination in the presence of an acid. So you can do this in a protic solvent with no problem. And it actually competes. Sometimes you'll have a little bit of competition between E1 and SN1, depending on what your nucleophile is for the SN1. If it has some basic properties as well, then you'll see a little bit of competition between SN1 and E1. Right, so this is the product. Right, and the sulfuric acid is always going to get regenerated. So let's talk about how it works, and then we'll talk about the characteristics of it. Right, so let me go back to the E2. One thing I didn't give you up here is the rate law. Of course, it's the 2, just like SN2 is bimolecular. So it's the base concentration and then the substrate concentration. Right, so it's a second order rate law, just like the SN2. So whatever you change about the base or the substrate is going to affect the overall rate. And then the way you facilitate it, you use stronger bases, tertiary substrates, which give you more stable products, and good leaving groups, right? Right, all those things facilitate that reaction. But so let's go back to the E1 and let's go through the mechanism. Right, again, this can be in a protic solvent. There's no base necessary. There's no geometric requirement necessary because you have a carbocation. So one intermediate. So that intermediate is where the elimination is going to happen. So if the leaving group is already gone, then you don't have to worry about the geometry being antiperiplanar or anything like that. All right, so let's go through how this works. So this is sulfuric acid. Right, and the first step is going to be a proton transfer, because you talked about OH before. It's a terrible leaving group. So you have to make it a better leaving group. So one way to do that is to protonate it and turn it into a hydronium. So this is coming here like, not like that. Right, and then I'm gonna put that pair of electrons onto oxygen. Let me put the other lone pairs in. All right. So what I get from that is this hydronium ion, which now has water as the leaving group, much better leaving group, and that's going to be in equilibrium with the carbocation intermediate. So once I lose the leaving group, this is the rate determining step. I have that plus water plus, let me draw that up here, the conjugate base of sulfuric acid. All right. All right, so now the question is, okay, so here's my carbocation. Let me make that look a little more presentable. And then my alpha protons are next door. Both sides are equally accessible. So it doesn't matter where you take the hydrogen from to do the elimination. But the question is, which of these two things is going to do the elimination? Like which one of them is going to act as your base? Because even though there's not a formal base present, you still need something basic to do proton transfer, right? So sometimes it can be your conjugate base from your acid or water. Water can be both an acid and a base, right? So, but for this case, we're just going to use the conjugate base from sulfuric acid. We'll use that as our base, right? So this is gonna come here, pull that proton off, right? And the electrons from that CH bond, that's what I'm going to use to make my pi bond. So this is now here like that. And these protons didn't get touched, so I'm gonna put them back. And apologize for the lag. Blame AT&T. So that's that plus water. And you reform sulfuric acid. All right. So the E1 again is there's no geometric requirement. right? You can do it in Proton. Proton solvents, and then you don't need a base, right? And it follows a similar pathway to SN1. All right. So we've gone through all four of these mechanisms: SN2, SN1, E2, E1. We know what to look for. As a matter of fact, I think I sent out one video, the ICE method, that helps you to figure out, helps you to look at a set of reaction conditions and determine whether or not the reaction is SN2, SN1, E2, or E1. So let's jump in. We got about 10 minutes left. So we're going to jump in and do a couple of these examples. Start. Yeah, let's start here. This is a good warm up. All right, so it says draw the substitution products for the reactions A and B. And then for reaction A, explain why the rate of reaction will not be affected when you increase the concentration of the nucleophile when the reaction is done in ethanol. Explain why the rate decreases when the solvent is switched from DMSO to ethanol in reaction B. So let's do that. So let's go to the first reaction. You're going to get the same product, so that's why it's only one line there for the product. So what is my substrate? What is my nucleophile? What is my solvent? So where's the substitution going to happen?
That's the OTS.
Yes. This leaving group right here is what it's called a tosylate. If we go up on our list, it's right here. Where is it? Toluene right here. It says OTS, toluene sulfonic acid. But for short, we call it a tosylate. So that's the tosylate anion. You can see the pKa, negative 0.6. So it's actually a really good acid. And that means it's going to also have the pKa of the conjugate acid. So that means that this is going to be a very good leaving group. All right. So the tosylate is my leaving group. And then over here, anytime you see sodium, that's a counter ion, right? It's positive. And so my nucleophile is going to be that, right? The OCH3 or the methoxy anion. All right. So now what's the product? We're not even going through the arrows. All right. We're just going to do the product. What would the product look like?
The OCH3 will be where the OTS was.
Yeah, it's a substitution, right? So the leaving group is going to get substituted with the nucleophile. Let me fix that up. And then just to keep track of everything, that's Na plus and OTS minus. All right, we don't really care about that, but it is what it is. So if I do this, this is a secondary carbon. All right. So that's the purpose of this example. This is that's a bad color. Sorry about that. right? So remember, secondary carbons, you can do SN2 or SN1. So what we have to look at is some other attribute of the reaction, some other characteristic, like the solvent or the nucleophile, but mostly the solvent. So if we look at the solvent, notice I have like two different solvents here. And that's just to illustrate the fact that the mechanism can be different based on the solvent, right? If it's done in an aprotic solvent, that's going to point to a SN2 type mechanism. If it's done in a protic solvent, it's going to point to a SN1 type mechanism, right? Because remember, protic solvents facilitate SN2, aprotic solvents facilitate SN2, protic solvents facilitate SN1. So let's read that question again. It says, explain why the rate of reaction will not be affected when you increase the concentration of nucleophile when a reaction is done in ethanol. Somebody help me with that question. If I do this reaction on this secondary allylic carbon in ethanol, what does that mean for the mechanism?
Nothing, because it only depends on the substrate.
Yes. So if I do it in ethanol, the rate, sorry about that. It's just K times the concentration of the substrate, because it's unimolecular. Remember that term, unimolecular, meaning the rate determining step is it only involves the substrate and not the nucleophile. Right up here is bimolecular. So that means that the rate is going to be dependent on both the nucleophile as well as the substrate. Right, and for E1, which I just realized that we didn't talk about the rate law, it's the same rate law as SN1, K times the concentration of the substrate. All right, so if I do it in ethanol, nothing happens to the rate because the nucleophile is not involved in that rate, right? Or not involved in the rate determining step. All right, okay, so let's look at the next one because I think the second question is asking about that. So if I do that second reaction, and this is a triflate leaving group. Right, it's a really good leaving group. Let's go back up to the chart. It is right here. Right, it's trifluoroacetate, which is the conjugate base of trifluoroacetic acid. All right, so the triflate, and you abbreviate that as OTF, lowercase f, sorry. It looks uppercase, but it's just my terrible handwriting. All right, so that's the triflate. And if you look at the pKa of the conjugate acid, that's also a very good acid. It has a pKa of 0.2. All right, so let's go back to here. We got a good leaving group. We have a cyanide nucleophile, and this is what we call a nitrile group, right? Carbon is negative. What is the product? What does the product look like? We know the chain is still intact, right? We're not touching that. But what if it's a substitution? What happens between the leaving group and the nucleophile?
It would just replace it.
Just replace it. That's it. And it's carbon that attacks, not nitrogen, even though nitrogen also has a lone pair. All right, so that question asks, Explain why the rate decreases when the solvent is switched from DMSO to ethanol in reaction B. So if I do it in DMSO, what mechanism do you think is going to predominate? This is a primary carbon.
SN2.
Yes. Right, it's on a primary carbon. A primary carbon will never do SN1, right? So DMSO is aprotic, so it's going to facilitate SN2 type reactions. Ethanol is protic, all alcohols are protic, so it's going to facilitate SN1 type reaction. All right, so this is SN2. So if I switch to ethanol, what do you think is going to happen to the rate? Or why does the rate decrease? Somebody help me with that. All right. What are the protons on the solvent going to do to your nucleophile? If you put a nucleophile like that, nitrile, in a protic solvent,
Salvation.
it's going to solvate the nucleophile, right? So if you switch from DMSO to ethanol, then your nucleophile is going to get solvated, right? That's what slows the rate down. Right? Anytime you run a reaction that you know is going to be a SN2 type reaction in a protic solvent, is going to solvate your nucleophile and decrease the rate because it's going to lower the energy of your nucleophile. We talked about that on I think on Friday. All right. Questions about that example? So on a primary carbon, that's one of the clues you look for when you're trying to determine whether a reaction is going to go SN2 or SN1. If it's on a primary carbon, it's a dead giveaway that it's going to be SN2. All right. Primary carbons do not do SN1 substitution. All right. Neither do sp2 carbons. You can't do substitution, period, on an sp2 carbon. You can only do addition followed by elimination. All right, let's go to the next question. We're going to stop on this one. What mechanistic pathway would you expect the following reactions to follow? And somebody tell me, let's point out all the factors, everything that's involved in this reaction, right? Is acetone protic or aprotic?
Is it protic?
Aprotic.
Say protic. If you look on the list up top, the first solvent listed on there is acetone. It's polar aprotic. Doesn't have any the only way you can get a proton from acetone is with a strong base to pull it off. But it's not protic. It doesn't just readily give up protons. The pKa of those acetone alpha hydrogens is like 19 or 20. So they're not just going to pop off. All right. So acetone is aprotic. And then look at your substrate. Is it primary? Is it secondary? Is it tertiary? And what I mean by that is the carbon where the Levy group is located.
Secondary.
Secondary carbon, good. You got a secondary carbon, an aprotic solvent, pretty good nucleophile, right? And then look at the product. What happened in the product that gives it away, gives the mechanism away?
Substitution.
Well, it's definitely a substitution, but it could be, since the carbon is secondary, right? It could be SN2 or SN1, But the fact that it's an aprotic solvent is a dead giveaway too. Because aprotic solvents, which mechanism do they facilitate?
SN2.
SN2. So what about the product? Look at the difference in the stereochemistry. Can you see that? How the product is dashed, but the star material where the carbon where the leaving group is wedged. Is that right? What do we call that when the stereochemistry changes like that?
Inversion.
Yes. So you have inversion of stereochemistry. You got an aprotic solvent. You have a secondary carbon. Of the choices, what would you pick?
C, SN2.
It's SN2. All those things give that away. I kind of gave it away earlier, but all those factors give it away. Inversion of stereochemistry, aprotic solvent, secondary substrate, good leaving group, all those factors point to that mechanism being SN2. All right, we're gonna stop here. We'll pick this up on Wednesday.